unlike light, which had seemed to have a good theory from classical electromagnetism, our understanding of matter itself was arguably much less advanced in the classical physics world of the 19th century. We certainly had a strong empirical understanding of many aspects of chemistry and the ideas of atoms and elements, but we really had no good idea of what atoms really were and where something like the periodic table of the elements, for example, actually comes from. Now, quantum mechanics solves these problems of understanding what matter is. Indeed, there is essentially nothing about the properties of materials that we can adequately explain from a basic point of view if we don't go back to quantum mechanics. We simply have to use quantum mechanics to explain most properties of materials. Why are some materials hard and others soft? For example, why can a diamond scratch almost anything, but a pencil lead will slide smoothly, leaving a black line behind it? And as you probably know, even more surprisingly, both the diamonds and the pencil lead are actually made from exactly the same element, carbon. The pencil lead is essentially graphite, that version of carbon. Why do metals conduct electricity and heat easily, but glass does not? Why is glass transparent? Why do metals reflect light? Why is one substance heavy and another substance is light? Why are some metals magnetic and others are not? And as I said, where does the periodic table of the elements come from? Now, to answer those questions, we need a good deal of science and other science, such as chemistry and materials science and many other branches of physics. Those questions are not easy to answer in any detail without going to those other sciences and that other body of knowledge. But in doing so, all of these sciences will rely on our basic quantum mechanical view of how materials are put together. The next step in this introductory history of quantum mechanics is the attempt to explain the behavior of the simplest of all elements. That's the hydrogen atom. Quantum mechanics solves this problem, and in doing so sets up our entire understanding of what the ordinary matter round about us actually is. When we heat up hydrogen, which is a gas under normal conditions, it emits light. But it does so only at a very specific set of wavelengths. These wavelengths extend from X-rays to the infrared. And we're showing in this picture here the lines that we can see in the visible part of the spectrum, and these form part of what is called the Balmer series. So for example, we see a red line, the hydrogen alpha line, at 656.3 nanometers for its wavelength. We see the hydrogen beta line as some sort of light blue-green color, the blue hydrogen gamma line, and the violet hydrogen delta line. Now, why does hydrogen emit only at these specific wavelengths? And this was well known at that time in the early 1900s. Many models were being discussed at the time for what hydrogen was really like. A very important intermediate model of the hydrogen atom is the so-called Bohr model. This model starts out by assuming that the electron is a particle that orbits around another particle, the proton, in much the same way that a planet orbits around the sun. But here we're relying on electrostatic attraction between the negatively charged electron and the positively charged proton, instead of the gravitational attraction we would see for an actual plane and an actual sun. Then comes Bohr's key assumption, which he published in 1913. Presume, for some reason not known, that the angular momentum of this electron can only take specific values. Angular momentum is that property that something has when it's spinning. It's like momentum, you retain it as you go forward unless there's some friction or something. Things keep on spinning. But what he was proposing here was that this angular momentum, which something like an orbiting electron would certainly have, can only exist in units of Planck's constant divided by 2 pi. Incidentally, this quantity, Planck's constant h divided by 2 pi, occurs so often in physics that we give it its own name and symbol. We call it h bar, and we write it as h with a line through the stem. In the Bohr model, we give each orbit a number, n, that we say also corresponds to the number of units of h bar of angular momentum in that orbit. This is a remarkable leap. Planck's constant was originally developed to understand something about light emission, Now we're applying it to the structure of matter. This model quite remarkably does give the energies of the spectral lines of hydrogen. They are the energies of the separations of these different orbits in energy. So if we go back to our set of lines, we can see this result explicitly. Now we find that the photon energies corresponding to these lines are these very specific ones that we've written on the view graph here, showing, for example, the transition from n equals 3 to n equals 2, being that red line in our Balmer series. And for the other lines here, they are, for example, the light blue line is from n equals 4 to n equals 2, and the darker blue line is from n equals 5 to n equals 2, and the violet line is from n equals 6 to n equals 2. So this understanding that we get from quantum mechanics, namely that the color here of the emission of light is associated with the energy separation of energy levels within materials, is the basic theory of why materials have the colors that they have. Once we understand the detail of quantum mechanics better, we can actually calculate these energy levels and how they interact with light. And as a result, we could figure out the color of some material. As we said then, this model successfully incorporates Planck's constant into the theory of matter. It also gets the approximate size of the hydrogen atom correct. That size is roughly 1/10 of a nanometer in diameter, or half that as the radius. Often for atoms we will use units that English speakers typically mispronounce as angstroms, and which correspond exactly to 1/10 of a nanometer. These units take the name of a Swedish scientist and should be pronounced Ångström or something like that. Again, I apologize for my pronunciation, which is of course his name. However, despite its remarkable success and its very substantial importance in the development of quantum theory, the Bohr model is not actually right in several ways. It does not quite get this angular momentum right, although the quantization in units of h-bar remains very important. It also appears to predict that the atom would be radiating electromagnetic radiation all the time because it's a spinning electron that we're whizzing around the nucleus here, the proton, and a spinning electron like that whizzing around in an orbit would be continually radiating electromagnetic energy and thus losing energy, and that just does not make sense here. And it gives an entirely incorrect picture of what the hydrogen atom actually looks like. A very important point is that the electron is not some small point in a classical orbit. It is, however, very, very difficult to get this picture out of people's minds. And to help counter that problem, here is what the hydrogen atom actually looks like. So these are calculations from the deeper quantum theory that we will get to of the hydrogen atom. And on the left, we see the n equals 1 state. It's actually a kind of a fuzzy ball. And one thing that is a surprise to many people, it actually has its highest density at the center of the ball. One of the next level of the hydrogen atom is shown on the right. Again, this looks nothing like a point electron in some classical orbit. And for those of you who are used to seeing these things perhaps in some chemistry class, the one on the right is what's called a p orbital of the hydrogen atom, and there are 3 of those. That's one in one direction, perhaps we'll call it the horizontal x direction, there's one in the y direction and one in the z direction. Okay. Anyway, we will come back to that later on. In his 1924 PhD thesis, Louis de Broglie, and that's a strange pronunciation for an English speaker, it's a French pronunciation of that spelling, but that's the guy's name, made a deceptively simple proposal. Just as it seemed that what we previously thought of as waves, namely light and electromagnetism, might also have particle properties, also specifically in that case the photon, he proposed that what we previously thought of only as particles might have wave properties. Specifically, he proposed that the wavelength of those waves would be Planck's constant divided by the momentum of the particle. And he noticed that you can actually put this back into the Bohr model to interpret the orbits of the Bohr model as kinds of standing waves. Now, we won't go any further with that here because it still does not sort out the Bohr model correctly in our modern understanding. But there is a core of truth in this specific idea when we apply it to atomic orbitals, and we'll get to that later on. Now, this idea of saying that, well, we had waves that we then decided were particles, that was light and the photon, then maybe if we've got particles, and specifically he was thinking of the ones that have mass, like electrons and so on, then we should think of those as waves. Well, with the success of this Bohr model and with de Broglie's hypothesis of the wave nature of the particle with mass, such as an electron, and as I said, that's a hypothesis that also seemed to fit to some degree with Bohr's model, the stage is now set for a much more comprehensive mathematical model of some kind. Maybe we're going to manage to sort all this out, rather than these very ad hoc models that don't seem to have proposals that come from anywhere in particular. Maybe we can construct something more comprehensive that really makes sense. And two models emerged independently at about the same time. So Werner Heisenberg first proposed a model for quantum mechanics based on matrices in 1925. Actually, at that time, he didn't really know about matrices, and he unwittingly reinvented matrices in all their mathematics to do this. This model looks quite abstract, and matrices, of course, are nowadays very common in a broad range of scientific and engineering calculations. But in 1925, they were still a very abstract branch of mathematics, and not really known to very many people. The other model here was Erwin Schrödinger's wave equation, developed in 1925 and published in 1926. Now, this model actually, on the face of it, looks more concrete. It proposes actual waves for matter, though in fact it was perhaps more abstract than we really realized at that time. And that's because it's not really all that clear exactly what those waves are, and what, if anything, they actually mean is one of the subtleties of quantum mechanics. Anyway, undoubtedly one of the major triumphs of Schrödinger's equation is the explanation of the hydrogen atom with the correct orbitals. Those ones that I showed you, those sort of clouds, are the result of solving Schrödinger's equation. And that understanding of the hydrogen atom and the work that follows from it provides our modern understanding of the basics of atoms and chemical bonding, and thus of all the major microscopic properties of matter. When we use quantum mechanics, we may be working with Schrödinger's equation, but in fact we're just as likely to be working with matrices, or equivalently writing Schrödinger's equation in a matrix form. And after some initial controversy between the Heisenberg and Schrödinger approaches, it was realized, by Schrödinger in fact, that these were actually quite equivalent. The Heisenberg model and the Schrödinger model were not in contradiction to one another. They were other ways of looking at the same mathematics. And we will see as we go forward here now that we use both of these, somewhat seamlessly moving between one and the other, because they are in fact the same thing. The mathematics of quantum mechanics was sorted out over the next several years by Heisenberg and Schrödinger, and a quite remarkable collection of other individuals, including Max Born, Pascual Jordan, Paul Dirac, and John von Neumann. And since we will be going through both of these approaches here, including how to move back and forward between them, we will not go into further details at the moment. But this quantum mechanics based on Heisenberg's and Schrödinger's formulations will form the basis for much of what we were going to discuss now. It's at the core of most of the applications of quantum mechanics in engineering, and also for the many basic phenomena in physics and other sciences.